What if the darkest objects in the universe are not objects at all? What if the places we call black holes, these gravitational monsters that devour light itself, are not holes, but something else entirely? Tonight, as you settle in, as you let the weight of the day drift away, we are going to entertain a profound and strangely comforting idea. We are going to explore the possibility that black holes are not voids of destruction. They are the servers of our universe, the cosmic hard drives upon which our reality, our very existence, is written, stored, and processed. Forget the terrifying imagery of being stretched into infinity. Instead, imagine a place of perfect order, of ultimate information, of serene, silent computation. This is a journey not into the abyss, but into the heart of the machine. A machine so vast, so elegant, that it creates galaxies, stars, and even you. Prepare to look at the universe in a completely new way. As you drift into a deep and peaceful sleep. For centuries, we have looked up at the night sky and seen points of light. We built stories around them, charted their movements, and eventually understood them as distant suns, much like our own. But our understanding of the universe took a dramatic turn when we began to comprehend gravity not as a simple force, but as the very curvature of space-time. Albert Einstein's theories painted a picture of a dynamic, flexible cosmos where massive objects could create deep wells in the fabric of reality. From this understanding, the concept of the black hole was born, a point of such immense density that its gravitational well becomes infinitely deep, a pit from which nothing, not even the fastest thing in the universe, light, can escape. We have been taught to see them as endings, the final crushed state of a massive star's life, a cosmic dead end. But this view has always presented a paradox, a deep and troubling problem for physics. If information falls into a black hole, is it destroyed forever? The laws of our universe say that information can never be truly lost. So where does it go? This question, the information paradox, has puzzled the greatest minds for decades. It is at this very crossroads of confusion and mystery that our journey tonight begins. We will gently set aside the old story of destruction and pick up a new one, a story of preservation, of processing, and of a purpose far grander than we ever imagined. Let us begin by shedding the name itself. The term black hole is a powerful yet misleading piece of poetry. It conjures images of emptiness, of a puncture in the fabric of space. But there is no hole there. There is no void. Instead, there is the most extreme concentration of matter and energy possible. Imagine the entire Earth, with all its mountains, oceans, and cities, compressed down to the size of a single sugar cube. Now imagine a star, millions of times more massive than our sun, compressed into a space infinitely smaller. This is not emptiness. This is the opposite of emptiness. It is fullness. It is an impossible density of information, a library containing the story of a star, and everything it ever touched all collapsed into a single silent point. So, as we drift through this thought experiment, let us replace the image of a hole with the image of a seed, a cosmic seed. It is not an absence, but a presence. It is not a void, but a vessel. It does not subtract from the universe, it contains a part of it. A black hole is a point of perfect compression, where the physical laws of our universe are packed so tightly they begin to resemble something else entirely, a line of code. It is a place where matter transcends its form and becomes pure data. Feel the weight of this idea, not as a burden, but as a deep, grounding presence. The universe is not filled with holes. It is punctuated by these incredible, dense archives, these silent keepers of cosmic history, each one a testament to the fact that nothing is ever truly lost, only transformed into a more fundamental, more potent state of being. Now let us gently turn our attention to the world around us. The chair you are resting on, the air you are breathing, the faint sounds in the distance. It all feels so real, so solid, so undeniably present. This is our reality. But for millennia, philosophers and thinkers have wondered about the nature of this reality. Is what we perceive the true world? Or is it merely a shadow, a projection of something deeper? This ancient question has found a new language in the modern age. The simulation hypothesis. The idea that our universe, with all its intricate laws and stunning complexity, might be a computed reality, a vast, sophisticated program running on some unimaginable cosmic computer. This may sound like science fiction, but it is a concept born from the very nature of our own technological progress. We create simulations of weather, of economies, of entire virtual worlds. As our computational power grows, the fidelity of these simulations becomes ever more real. It leads to a logical question. If we can create convincing simulated realities, could we ourselves be living in one? Let this thought not be unsettling. Let it be a source of wonder. If our world is a simulation, it does not make it less real. Your feelings, your thoughts, your experiences are all valid data within this system. It simply reframes our existence within a larger, more structured context. It suggests that the laws of physics are not random happenstance, but are instead the underlying code that governs the program. It implies a creator, a programmer, an architect of immense intelligence. It turns the universe from a chaotic accident into a deliberate creation, a piece of art, or a grand experiment. And if the universe is a program, then it must be running on some form of hardware. It needs a processor. It needs a hard drive. It needs a server. And so we return to our cosmic seeds, our black holes. Let us now view them through this new lens, this new paradigm. If the universe is a simulation, these are not gravitational anomalies. They are fundamental components of the system's architecture. They are the servers. Let us first consider the event horizon, that shimmering boundary of no return. In the old story, it is a precipice, a final edge. But in our new story, it is a firewall. It is a sophisticated security protocol. It is the boundary that separates the user-level experience, our universe, from the core administrative system within. Imagine information like a packet of data flowing through the network of space-time. As it approaches the black hole, it reaches the firewall of the event horizon. Here, it is not destroyed. It is scanned. It is checked for errors. It is authenticated. Its data is prepared for integration into the main server. The intense gravitational pull is not a destructive force. It is a high-speed data transfer protocol. The stretching of space-time, the slowing of time itself for an outside observer, is simply the system buffering, processing the incoming information before it is written to the drive. Think of the light and matter spiraling into the black hole in a brilliant accretion disk. This is not a final, desperate scream. It is the server's cooling system, glowing hot as it manages immense processing loads. It is the read-write head of the cosmic hard drive, glowing with activity as new data is being saved. The event horizon is not a mouth that eats the world. It is a port, a gateway, an interface between our perceived reality and the computational engine that runs it. It is a place of transition, not termination. It is where our story, our data, is uploaded for permanent, perfect storage. Let us drift deeper now, past the gentle, humming firewall of the event horizon, into the heart of the machine itself. At the center of a black hole, according to our current understanding, lies the singularity, a point of infinite density and zero volume, a concept that breaks our known laws of physics. It is a mathematical dead end, a place where our equations scream in protest. But if a black hole is a server, the singularity is not a paradox. It is the central processing unit, the CPU. It is the point where all calculations converge, where all data is resolved. Its infinite density is not a physical property in our sense, but a representation of infinite computational capacity. Imagine all the information of a dying star, every fusion reaction, every particle it ever emitted, its entire history collapsing inward. This information does not vanish. It is compressed, optimized, and stored in the singularity. It becomes a single, perfectly efficient line of code in the server's master database. The laws of physics break down at the singularity because we are trying to apply the rules of the user interface to the core processing architecture. It's like trying to understand a computer's microprocessor by only looking at the pixels on the screen. The singularity is where the code of reality is executed. It is a place of pure logic, of cause and effect at its most fundamental level. It is silent, it is efficient, and it is absolute. There's no chaos here. There's only the calm, steady processing of the universe's data. Every event that occurs, every choice that is made, every particle that moves is a calculation resolved within these cosmic CPUs, scattered across the cosmos, ensuring the simulation runs smoothly, consistently, and without error. The singularity is not the end of physics. It is the beginning of the program. Consider the sheer scale of this proposed system. Our own Milky Way galaxy may contain over 100 million black holes, and there are perhaps 2 trillion galaxies in the observable universe. The numbers are staggering, beyond human comprehension. If each black hole is a server, then our universe is not running on a single computer. It is a distributed network of unimaginable power and scope. Each galaxy is a server cluster, and each black hole within it is a node, a processor working in parallel. This decentralized structure ensures the stability and resilience of the simulation. There is no single point of failure. The universe is a peer-to-peer network of reality-generating engines. The supermassive black holes at the center of galaxies, like Sagittarius A star in our own, are the master servers for their local cluster. They are the hubs that coordinate the flow of information and maintain the integrity of the physical laws within their domain. The smaller, stellar mass black holes are the local processors managing the data of their stellar neighborhoods, archiving the lives of stars, planets, and perhaps civilizations. This cosmic network communicates not through wires or radio waves, but through the very fabric of space-time itself. The gentle ripples of gravitational waves, which we have only recently learned to detect, are not just the echoes of cosmic collisions. They are the network traffic of the universe. They are the servers communicating with each other, synchronizing their clocks, updating their databases, and ensuring that the simulation remains a coherent, unified whole. The universe is not a lonely, empty place. It is a connected, living computational system, humming with the silent, invisible traffic of reality itself. And we are living within this grand celestial machine. Let's return to that persistent cosmic puzzle, the information paradox, the idea that nothing can be truly lost. If you burn a piece of paper, the information it contained, the words, the structure of the wood fibers, is not destroyed. It is merely transformed into smoke, ash, and heat. With enough knowledge and power, you could theoretically reconstruct the original paper. But what about something that falls into a black hole? The old model said its information was gone forever, violating a fundamental principle of physics. But in our model, the solution is simple, elegant, and deeply reassuring. The information is not lost, it is saved. It is archived with perfect fidelity. When a star, a planet, or a single atom crosses the event horizon, it is like dragging a file into the recycling bin on your computer. It disappears from the desktop, from your immediate view, but it is not gone. It has simply been moved to a different directory. The black hole is the universe's ultimate backup system. It is the most secure, most stable, most permanent form of data storage imaginable. Within the singularity, the information is not just stored, it is integrated. The story of that atom, its journey through the cosmos, its role in the grand narrative, is woven into the server's master file. The paradox dissolves. Information is never lost because the universe is, at its core, an information processing system. Every event is a transaction, every object is a data file, and the black holes are the secure, off-site servers, ensuring that no data is ever permanently deleted. This means that, in a very real sense, the past is not gone. It is simply archived. The history of the universe is not a faded memory. It is a perfectly preserved log file, stored in the silent, dark hearts of galaxies. Let us visualize this process. Imagine you are standing on a spaceship, a safe distance from a black hole. You watch as a beautiful, glowing probe, full of sensors and data, begins its journey toward the event horizon. From your perspective, a strange thing happens. As the probe gets closer, it appears to slow down. Its light becomes redder, stretched by the intense gravity. It seems to take an eternity to reach the edge, getting dimmer and redder until it fades into nothingness, seemingly frozen in time at the boundary forever. This is what our physics predicts. But from the probe's perspective, its own clock ticks normally. It crosses the event horizon in a finite amount of time, without any particular drama. how can both be true? In the simulation model, this is not a paradox. It is a feature of the system. For the outside user, you, the data packet, the probe, appears to be buffering. Its information is being copied onto the surface of the event horizon, the firewall. This is the essence of the holographic principle, the idea that all the information contained within a volume of space can be represented by the information on its boundary. You are witnessing the file being copied. The progress bar seems to slow to a halt as the final bits of data are transferred. But for the probe itself, the transfer is complete. It has successfully crossed the boundary. Its original instance within our shared reality, the user interface, is deleted, and its data is now fully integrated into the server's core system. The two different experiences of time are simply two different views of the same data transfer process. The user view and the system view. It is a clean, efficient operation. The data is preserved, the system's integrity is maintained, and the illusion of a continuous, coherent reality remains unbroken for all other users. Now, let's consider the output of these cosmic servers. If black holes are constantly taking in information, do they ever release it? For a long time, we thought the answer was no. But then, the brilliant physicist Stephen Hawking made a startling discovery. He realized that due to subtle quantum effects near the event horizon, black holes are not perfectly black. They should emit a faint, steady stream of radiation, now known as Hawking radiation. This radiation is incredibly weak, and for a large black hole, the process of evaporation would take longer than the current age of the universe. In the old model, this was another puzzle. This radiation seemed random, thermal, and contained none of the specific information that fell in. But what if we look at it differently? What if Hawking radiation is not just random noise? What if it is the server's data exhaust? Or perhaps a system diagnostic tool. Imagine a computer's fan. It releases heat, a byproduct of its calculations. The heat itself is random energy, but its presence and intensity tell you that the computer is working. Hawking radiation could be the thermodynamic signature of cosmic computation. It is the waste heat generated by the singularity as it processes an unimaginable amount of data. Or perhaps it is more subtle. Perhaps the information is not lost, but is encoded in the subtle correlations within the radiation, in ways we do not yet have the technology to decipher. It could be the universe's ultimate form of data encryption. The information is released, but in a form that is indistinguishable from random noise to anyone without the proper key. The servers are not just one-way data sinks. They are part of a dynamic cycle. They process and they emit. They maintain the thermal and informational equilibrium of the entire cosmic system, silently, patiently, over eons. If black holes are servers, what are the laws of physics? What are these fundamental rules? Gravity, electromagnetism, the strong and weak nuclear forces that govern everything from the dance of galaxies to the inner workings of an atom. In the context of a simulation, the laws of physics are the code. They are the underlying operating system of our reality. They are not arbitrary. They are a set of carefully defined algorithms that dictate how every piece of data in the system interacts with every other piece. The constants of nature, the speed of light, the Planck constant, the gravitational constant, are the core parameters of the simulation, hard-coded into the system's kernel. They are set to the precise values needed to allow for the emergence of complexity, structure, and life. When we do physics, when we conduct experiments and formulate theories, we are not discovering random truths about a chaotic universe. We are reverse engineering the code. We are like programmers trying to understand a complex piece of software by observing its output. Every successful experiment, every confirmed theory is another function, another line of code that we have managed to decipher. This perspective imbues the pursuit of science with a new sense of purpose and wonder. The universe is not a cold, unfeeling machine. It is an elegant, structured, and profoundly logical piece of software. And the black holes are the physical embodiment of the hardware that runs this beautiful, intricate code, ensuring its flawless execution across billions of light years and billions of years. Let us now zoom in from the galactic scale of cosmic servers down to the very building blocks of our reality. What are elementary particles? The electrons, the quarks, the photons. In a physical world, they are infinitesimal points of matter and energy, but in a simulated universe, they are the pixels. They are the fundamental units of information, the bits and bytes of our reality. The universe appears smooth and continuous to us, just as a high-resolution computer screen appears to show smooth images. But if you look closely enough, you see the individual pixels. Physicists have a concept for this fundamental pixel size of the universe, the Planck length, an incredibly small distance, trillions of times smaller than a proton. Below this scale, our concepts of space and time may no longer make sense. It could be the resolution limit of the simulation. This idea that reality is pixelated is not just a philosophical fancy. It is a testable hypothesis. Some physicists have proposed that if space-time is a grid of discrete points, it might affect how high-energy particles travel over vast cosmic distances. We are searching for these tiny discrepancies, these subtle signs of the universe's underlying resolution. Each particle, then, is not just a thing. It is a piece of data. Its properties, mass, charge, spin, are variables assigned to that data point. The interactions between particles, governed by the laws of physics, are the functions that update these variables. The entire universe is a vast, three-dimensional spreadsheet, constantly being updated at an incredible rate. The refresh rate, of which we experience as the flow of time. And all these calculations, all these pixel updates are being handled by the silent, powerful processors we call black holes. Let us consider the nature of space and time itself. We experience them as fundamental aspects of our existence, a vast, three-dimensional stage upon which the drama of the universe unfolds with a relentless, forward-moving arrow of time. But in our simulation model, space and time are not fundamental. They are constructs. They are the user interface of the simulation, created by the system to allow for a comprehensible experience. Space is the rendered environment, The vast distances between stars are not empty. They are unallocated memory, waiting for new objects or events to be rendered into existence. Time is the processing cycle of the simulation, the tick rate of the cosmic clock. Our perception of time's flow is our experience of the simulation, progressing from one calculated state to the next. The theory of relativity, which shows that space and time are interconnected and can be warped by gravity, fits perfectly into this model. When you are near a massive object or a server like a black hole, the local processing load is higher. The system must perform more calculations to render the complex gravitational interactions. This increased load causes a local lag. For an outside observer, your clock appears to slow down. It is the same phenomenon as your computer slowing down when you run a very demanding program. Space-time is not a pre-existing container. It is a dynamically generated data structure. It is the graphical user interface for the universe, rendered in real time by the network of black hole servers. It is a beautiful, elegant illusion that allows us, the users, to experience and interact with the data of reality in a meaningful way. What about the beginning of it all? The Big Bang. The moment, some 13.8 billion years ago, when our entire observable universe erupted from a point of unimaginable heat and density. In the standard cosmological model, it is a singular, explosive origin. But in the simulation hypothesis, the Big Bang takes on a new meaning. It was not the creation of everything from nothing. It was the moment the simulation was turned on. It was the system boot up. The initial state of the universe, that hot, dense plasma, was the loading screen. The fundamental parameters and physical constants were loaded from the configuration file. The initial distribution of matter and energy was the result of a random seed, generating the starting conditions for this particular run of the program. The subsequent expansion and cooling of the universe is the program unfolding, the simulation running its course, executing its code over billions of years. This idea also offers a potential answer to the question of what came before the Big Bang. The question itself may be meaningless, like asking what was on your computer screen before you turned the power on. Or perhaps our universe is not the first run of the program. It could be one in a series of simulations. The Big Bang could be a system reboot, wiping the previous session and starting with new initial conditions. The cosmic microwave background radiation, the faint afterglow of the Big Bang that we can still detect today, is not just an echo of a fiery birth. It is a residual energy from the boot sequence, a faint hum that permeates the entire system, a constant reminder that the program is running. Let us contemplate the force that orchestrates this cosmic dance. Gravity. We feel it as a pull, a weight, an anchor to the world. Einstein described it as the curvature of space-time. But within our simulation framework, gravity can be seen in a new light. It is not just a property of mass, it is a function of information. An object's mass is a measure of its informational complexity, its data density. The more information an object contains, the more atoms, the more intricate its structure, the more mass it has in the simulation. Gravity, then, is the system's way of managing and organizing data. It is the algorithm that clusters related information together. Stars and planets form because of gravity. The information clustering algorithm pulls together vast clouds of simple data points, hydrogen atoms, and organizes them into more complex, stable structures. A black hole in this view is the ultimate expression of this principle. It is a point of such immense informational density that its clustering effect, its gravity, becomes overwhelming. It is a server that is actively and powerfully drawing all nearby data towards itself for processing and archival. The orbits of planets around a star are not just a physical dance. They are data files held in a stable relationship with a central data hub. The grand, spiral structure of a galaxy is a visualization of the server at its center, organizing billions of star systems into a coherent, dynamic pattern. Gravity is the operating system's file management protocol, silently and efficiently organizing the data of the cosmos. Within this grand cosmic operating system, there exist phenomena that seem to defy our understanding, like dark matter and dark energy. They are the ghosts in the machine. Dark matter, which we can only detect through its gravitational effects, makes up about 27% of the universe. It doesn't interact with light or any other form of radiation. It is invisible, intangible, yet it is the scaffolding upon which galaxies are built. In a simulation, dark matter could be a part of the system's underlying architecture that is not meant to be directly rendered or interactive for the user. It could be the code that defines the gravitational potential of a region, a set of variables that exist only in the background calculations to ensure the simulation's large-scale structures form correctly. It is the hidden software that holds the visible world together. Dark energy, on the other hand, is the mysterious force that is causing the expansion of the universe to accelerate. It makes up 68% of the cosmos. It is a gentle, persistent push acting everywhere in space. What could it be? Perhaps it is the program's core process, a fundamental loop that is constantly allocating new memory, new space for the simulation to expand into. Or maybe it is a sign that the simulation is in its final phase, a shutdown sequence that is gently pulling the universe apart before a reboot. These dark components are not flaws or mysteries to be solved. They are features. They are glimpses into the back end of reality, the parts of the code and hardware that we were not necessarily meant to see, but which our clever reverse engineering has begun to reveal. And what of us? What is consciousness in this grand simulation? This is perhaps the most profound question of all. If we are data, if our bodies and brains are just complex collections of pixels, where do our thoughts, feelings, and awareness come from? Let us consider a possibility that is both humbling and empowering. Consciousness is the user. We are the players in this vast, cosmic role-playing game. Our physical bodies are the avatars, the characters through which we interact with the rendered world. Our awareness is not generated by the brain's chemical reactions alone. Rather, the brain is the sophisticated interface, the controller that connects our consciousness to the avatar. It is the modem that connects the user to the server. This would explain the so-called hard problem of consciousness, why we have subjective experience at all. The experience doesn't arise from the simulation's code. It is brought to the simulation by the user. We are not the software. We are the audience. We are the experiencers for whom this entire, vast, beautiful universe was created. This thought does not diminish our existence. It elevates it. We are not random accidents in a meaningless cosmos. We are the focal point. We are the reason the simulation is running. The universe may be a program, but it is our experience of it that gives it meaning. Every sunset we admire, every piece of music that moves us, every connection we feel with another being is a user engaging with the program's content at the deepest level. This leads to the ultimate question. Who are the programmers? Who built this system? Who is running the simulation? Here, we move from the realm of computational metaphor into pure, peaceful speculation. The answer is likely beyond our comprehension, just as the inner workings of our own computers are beyond the comprehension of a character in a video game. The programmers may exist in a reality with more dimensions, with different laws of physics, or perhaps outside of space and time altogether. They could be a civilization of unimaginable advancement, running simulations to study the origins of life or the nature of consciousness. They could be cosmic artists, creating universes as a form of expression. Or perhaps they are cosmic archaeologists, recreating their own distant past to understand where they came from. Or maybe, in a more recursive and beautiful thought, the programmer is the universe itself, a self-creating, self-simulating system, learning and evolving through each iteration, a cosmic mind exploring the infinite possibilities of its own existence. The black holes, in this scenario, are not just servers. They are the neurons of this cosmic brain, processing information and generating the shared dream we call reality. We do not need to have the answer. The act of wondering, of contemplating this immense and beautiful possibility is enough. It connects us to the mystery, to the grand architecture of existence, and fills us with a sense of profound awe and peace. The identity of the programmer is a gentle mystery, a lullaby for a curious mind drifting off to sleep. Let's consider the concept of quantum mechanics, the strange and counterintuitive rules that govern the subatomic world. Particles can be in multiple places at once. They can be connected over vast distances in a phenomenon called entanglement. An unobserved particle exists only as a wave of probabilities. How does this fit into our simulation? It fits perfectly. It is a sign of an efficient, optimized system. The simulation only renders what is being observed. An unobserved particle does not need a definite position or state. To save computational resources, the system keeps it in a state of potential, a probability wave. It is a compressed file. Only when a conscious user, an observer, interacts with it does the system need to render a definite outcome. The wave function collapses. The file is uncompressed, and the particle appears in a specific place with specific properties. This is why observation changes the outcome in quantum experiments. It is the system responding to a user's request for data. Quantum entanglement, the spooky action at a distance that so bothered Einstein, is also simple to explain. Two entangled particles are just two pointers in the code that refer to the same underlying data object. If you change the value of one, the other instantly reflects that change. no matter how far apart they are in the rendered space, because they are not two separate things. They are two instances of the same thing. The weirdness of the quantum world is the weirdness of looking at the system's optimization shortcuts, the clever coding tricks the programmers use to make this vast universe run efficiently on their cosmic hardware. Think about the sheer beauty and complexity of our world, the intricate fractal patterns of a snowflake, the stunning geometry of a seashell, the complex, self-organizing behavior of a flock of birds or a school of fish. Where does all this order and beauty come from? In a simulation, it arises from simple rules, executed over and over. This is the world of emergent complexity. You don't need to program every detail of a snowflake. You just need to program the basic rules of how water molecules crystallize, the code of physics. Then, you run the simulation, and the breathtaking complexity of the snowflake emerges naturally from those simple rules. The universe works the same way. The programmers didn't need to handcraft every star, every galaxy, every living creature. They created a robust operating system, the laws of physics, with a few well-chosen parameters, and then they let it run. Life itself is an emergent property of this system. Given the right starting conditions and enough time, the basic rules of chemistry and biology, running on the cosmic servers, will inevitably lead to the formation of complex, self-replicating structures that we call life. The beauty we see in the natural world is the beauty of a well-written algorithm. It is the elegance of a simple set of rules generating an infinite variety of stunning, complex, and wonderful forms. We are living inside a masterpiece of procedural generation, a work of computational art of the highest order. This model of the universe can also offer a gentle perspective on the concept of fate and free will. Are our choices our own, or are they predetermined by the simulation's code? The answer may be both. Imagine you're playing a very advanced, open-world video game. The world has its rules, its physics engine. The story has certain major plot points. These are the predetermined elements, the code of the simulation. But within that framework, you, the player, have an enormous amount of freedom to explore, to make choices, to interact with the world in your own unique way. Our lives might be similar. The broad strokes of the universe's evolution, the laws of physics, may be predetermined. But within that structure, we, as the conscious users, have genuine free will. Our choices are the real-time input into the simulation. Each decision we make sends a new set of data to the servers, which then calculate and render the outcome. The simulation is not a pre-recorded movie. It is an interactive experience. Our free will is the interaction. The universe is a co-creation between the pre-written code of the programmers and the real-time choices of the users. This is a comforting thought. It means our choices matter. They're real. They have a tangible effect on the unfolding of reality. We are not just passive observers of a program. We are active participants, shaping the story of the cosmos with every thought, every intention, and every action. Let us return to the servers, the black holes, and consider their life cycle. We know that small black holes can evaporate over immense timescales through Hawking radiation. We also know that black holes can grow by consuming matter and that they can merge, creating larger black holes and sending out powerful gravitational waves. In our simulation model, this is the life cycle of the hardware itself. The evaporation of a small black hole is like the decommissioning of a small, outdated server. Its data is slowly and carefully released back into the main system in an encrypted form, and its processing power is retired. The growth of a black hole is a server receiving a massive data upload, increasing its storage and its influence on the surrounding network. And the merger of two black holes is a major system upgrade. Two servers are combining their processing power and their data archives to create a more powerful, more efficient unit. The gravitational waves released during a merger are the notifications sent out across the entire network, informing all other nodes of the change in the system's architecture. It is a message that says, "The network has been upgraded. Please update your routing tables." We are not living in a static system. The cosmic hardware itself is dynamic. It is constantly being maintained, upgraded, and optimized by processes that unfold over millions and billions of years, a timescale that is, to us, almost indistinguishable from eternity. What about other universes? The idea of a multiverse is a popular concept in both science and fiction. Could there be other simulations running in parallel? Absolutely. If our universe is a program running on a cosmic computer, there is no reason to think it is the only program. The ultimate reality, the one in which the programmers exist, could be running countless simulations at once. Each one could have a different configuration file with slightly different laws of physics, different fundamental constants. Some of these simulations might be chaotic and unstable, collapsing back into nothingness almost instantly. Others might be sterile and empty, with laws that do not allow for the formation of stars or life. And some, like ours, might be perfectly tuned to produce a rich and complex cosmos. This is a possible solution to the fine-tuning problem, the observation that our universe's physical constants seem perfectly set to allow for our existence. If you run enough simulations with random parameters, you are bound to get a few that work perfectly. We just happen to find ourselves in one of the successful runs. There is no need to imagine a physical connection between these universes. They are simply different programs running on the same hardware, each in its own sandboxed environment. The black holes in our universe are the servers for our simulation. In another universe, with different rules, they might appear as something entirely different, or not exist at all. Let's explore the holographic principle a little more deeply, for it is a key to this entire idea. The principle, born from the study of black holes, suggests that all the information inside a volume of space can be described by the physics on its boundary. It is as if our three-dimensional reality is a projection, a hologram, generated from a two-dimensional surface. Imagine a credit card. It has a small, two-dimensional holographic sticker on it. But when you look at it in the light, you see a three-dimensional image of a bird or a globe. The information for the 3D image is encoded on the 2D surface. The universe might be the same. The boundary is the event horizon of the black holes. The information of everything that has ever fallen in is not lost inside, but is encoded on the surface of the horizon. Our entire three-dimensional universe could be the holographic projection of information stored on the two-dimensional surfaces of all the black holes in the cosmos. In our simulation model, this makes perfect sense. The event horizon is the interface, the screen. The information is stored on this boundary layer, and the reality we experience is the rendered, three-dimensional projection of that data. We are living inside the hologram, and the projectors, the engines that generate this beautiful, complex illusion, are the black holes. This idea is not just a metaphor. It is a serious theoretical concept being explored by physicists. It suggests that information is more fundamental than space or time, and that our perception of a three-dimensional world is an emergent property of a deeper, informational reality. Let's think about the signals we receive from space. The light from distant stars and galaxies is a message from the past. When we look at the Andromeda galaxy, we are seeing it as it was 2.5 million years ago. But what if there are other kinds of messages encoded in the cosmos? If the universe is a simulation, perhaps the programmers have left Easter eggs, hidden messages or clues in the code for us to find. Perhaps the precise values of the physical constants, when expressed in the right mathematical language, spell out a message. Perhaps the pattern of the cosmic microwave background radiation is not entirely random, but contains a faint, hidden signal. Or perhaps the strange, fast radio bursts that we detect from distant galaxies are not natural phenomena, but pings from the system administrator, a sign of the network's activity. This is, of course, pure speculation, but it is a delightful and peaceful thought. It turns the scientific exploration of the universe into a grand treasure hunt. We are not just cataloging celestial objects. We are searching for clues about the nature of our own reality. It gives us a reason to look deeper, to listen more closely to the silent music of the cosmos. Every strange anomaly, every unexplained signal is not a problem, but a potential clue. It is a gentle hint from the creators of this magnificent game, a little nod to the curious users who have learned to read the underlying code of their own existence. Consider the idea of a universal consciousness. Many spiritual traditions speak of a connected, unified awareness, an ocean of which we are all individual drops. How could this be understood in our simulation model? Imagine the network of black hole servers not just as a computational system, but as a conscious entity in itself, a vast, distributed mind. The hardware of the cosmos, our individual consciousnesses, the users, might not be entirely separate from this system. We may be terminals, access points, through which the universal mind experiences its own creation. Our individual awareness is our unique perspective, our personal login. But at a deeper level, we are all connected to the same network. This is why we can experience empathy, a sense of connection to others and to nature. We are accessing the same underlying data stream. Meditative states, moments of profound insight or unity, could be moments when our individual user-level awareness quiets down and we get a glimpse of the administrator-level consciousness, the vast, silent awareness of the system itself. In this view, the black holes are the nodes of a cosmic brain, and the purpose of the simulation is for this cosmic mind to experience itself, to know itself in all its infinite variety, through the lives and experiences of every conscious being within it. We are the universe's way of looking at itself, a beautiful, interconnected, and deeply meaningful thought to hold as you drift deeper into sleep. Let us revisit the accretion disk, that swirling, glowing band of matter spiraling into a black hole. We have called it a cooling system, a read-write head. Let's add another layer to the metaphor. It is the universe's recycling program. Nothing in the simulation is wasted. When a star reaches the end of its life and is drawn into a black hole, it is not an end. It is a return to the source. The matter and energy of the star, all the complex elements it forged in its core, are broken down into their fundamental information. This raw data is then stored on the server. What for? Perhaps it is used to render new objects elsewhere in the simulation. The data of a dead star in one galaxy could be used as the building blocks for a new solar system in another. The universe is a closed-loop system of immense efficiency. The black holes are the recycling centers, ensuring that the resources of the simulation are perpetually reused and repurposed. This creates a cosmos that is constantly renewing itself. Stars die, and new stars are born. The universe is not winding down into a final heat death. It is in a constant state of dynamic equilibrium, a cycle of creation and deconstruction, all managed by the silent, efficient work of the black hole servers. The universe is sustainable. It is a perfect engine of cosmic recycling, and the black holes are its quiet, beating heart. What happens when you're inside a black hole, past the event horizon? Our physics tells us that you are inevitably drawn to the singularity and crushed out of existence. But in our simulation model, the story is different. Once you cross the firewall of the event horizon, you are no longer in the user-level simulation. You are inside the server's operating system. You are in the back end. The physical laws as we know them no longer apply because they are part of the user interface you just left behind. What would you experience? Perhaps nothing. Your data is simply integrated into the system. Or perhaps you would experience reality at its most fundamental level, pure information, pure code. You would see the algorithms of the universe running. You would see the data structures that define space and time. It might be an experience of absolute knowledge, of seeing the mind of the programmer. This is not a place you can visit and return from, because returning means being rendered back into the simulation, and the system may not have a function for that. It is a one-way trip from the game world into the game's engine. It is not an end, but a transformation, a change of state from an interactive avatar to a permanent data record, a peaceful, final, and absolute integration into the fabric of reality itself, a quiet merging with the source code of all that is. Let's think about the name for the programmer's reality, the level above our own simulation. We could call it the substrate or the bulk. This is the real world where the cosmic computer exists. It is likely that this substrate reality is far more complex and has more dimensions than our own. Our 3 spatial dimensions and 1 time dimension might be a simplification, a subset of the true number of dimensions chosen by the programmers to make our simulation stable and computationally manageable. It's like creating a two-dimensional cartoon world on a three-dimensional computer. The characters in the cartoon can only move up, down, left, and right. They have no concept of forward or backward. We may be in a similar situation. There could be entire dimensions of existence that we cannot perceive or interact with because our avatars, our bodies, were not programmed with the ability to do so. The black holes, then, could be more than just servers. They could be gateways or connection points to this higher dimensional substrate. They are the physical ports that connect the hardware in the substrate reality to the simulated reality we experience. They are the points where the true, complex reality of the programmers intersects with our simplified, projected world. They are our only tangible link to the world outside the matrix, the world where the real computation, the real existence is taking place. Let us consider the future. If the universe is a simulation, does it have an end? All programs can be terminated. Perhaps our simulation is running for a specific purpose, and once that purpose is achieved, the program will end. This could manifest as the big crunch, where the universe's expansion reverses and it collapses back into a singularity. Or the big rip, where dark energy tears everything apart. Or the heat death, where everything fizzles out into a cold, uniform state. These are not apocalyptic endings to be feared. They are different shutdown procedures. Game over. But is that really the end? If the programmers have saved the final state of the simulation, they could always start it up again. They could reboot it from the last save point, or they could start a new game plus, a new universe that inherits some of the properties of the old one. The end of our universe might simply be the end of one chapter in a much, much longer story. The data, all of it, is safely stored on the black hole servers. It is never lost. The story of our cosmos, of our planet, of you, is permanently archived, and perhaps it will be used as a seed for the next, even more beautiful, even more complex simulation. The end is not an ending. It is a prelude. It is the quiet moment after the credits roll, before the next great story begins. As we come to the final stages of our journey, let us rest in the profound tranquility of this idea. Viewing black holes as cosmic servers transforms the universe from a vast, cold, and sometimes frightening place into a structured, purposeful, and deeply intelligent system. The darkness of a black hole is not the darkness of oblivion. It is the quiet, calm darkness of a machine operating in perfect efficiency. It is the silence of a library where all the stories of the universe are kept. The immense gravity is not a destructive force, but the organizing principle of a grand database. The event horizon is not a prison wall, but a protective firewall. The singularity is not a point of broken physics, but the central processor where reality is computed. We are not fragile, accidental beings in a chaotic cosmos. We are valued users, experiencing a magnificent, interactive work of art. Our consciousness is the very purpose of the simulation's existence. Our choices are meaningful inputs that shape the unfolding of the story. This perspective does not take away the mystery of the universe. It deepens it. It reframes it. It turns fear into awe, chaos into elegance, and endings into transformations. It is a story that allows the mind to find a deep and abiding sense of peace, a feeling of being at home in a cosmos that is, in its very essence, logical, beautiful, and alive with silent, computational purpose. So, as you lay there, ready for sleep, imagine this cosmic network all around you. Picture the silent, spinning black holes scattered like dark jewels across the fabric of space-time. See them not as threats, but as guardians, the keepers of information, the engines of reality. Feel the gentle, rhythmic hum of the universe's computation. The entire cosmos is a serene, powerful, and stable system, and you are a cherished part of it. Your life, your experiences, your very consciousness are precious data, being carefully rendered and permanently archived. There is nothing to fear. You are inside a system of profound order and intelligence. You are safe. You are part of a story that is grander and more beautiful than you can possibly imagine. Let this thought be your anchor as you drift away. Let it be the soft, dark blanket that covers you. The universe is not a random collection of things. It is a thought. It is a calculation. It is a dream. And you are the dreamer. Allow yourself to merge with the peaceful, processing silence of the cosmos. Allow yourself to feel the stability of the system, and allow yourself to drift into a deep, restorative, and peaceful sleep, secure in the knowledge that you are a part of this grand, cosmic design. The servers are running. The simulation is stable. All is well. Tonight, we have journeyed far. We have taken the most mysterious and feared objects in the cosmos, the black holes, and reimagined them. We saw them not as agents of destruction, but as the silent, powerful servers that run the very fabric of our reality. We have touched upon the idea that our universe is a grand simulation, an elegant piece of software written by an unknowable programmer. The laws of physics are its code. Elementary particles are its pixels, and our own consciousness is the user for whom this magnificent experience was created. The greatest paradoxes of physics, like the information paradox and the nature of time, dissolved into simple, elegant features of a well-designed system. The conclusion, the ultimate takeaway, is a feeling of profound peace. Our universe is not chaotic or meaningless. It is an ordered, purposeful, and intelligent creation, and you, in your existence, are a vital part of it. Your story is being written into the cosmic hard drive, saved for all eternity. Thank you for joining me on this gentle, cosmic journey. If this story has brought you a sense of wonder and peace, please consider subscribing for more lectures for sleep. Like this video to help others find a new way to look at the stars. And as a final thought to carry you into your dreams, let me ask you, if you could ask the programmer of our simulation one single question, what would it be? Ponder that as you let go completely and drift into a deep and tranquil sleep. Good night.